Welcome to an in-depth journey through the incredible evolution of atomic structure, from early philosophical ideas to the complex world of quantum mechanics. Today, we trace the scientific breakthroughs that revealed the true nature of matter. We begin with the fundamental concept, the atom. For centuries, it remained an invisible, theoretical building block, but modern science has uncovered its intricate structure, showing us the nucleus and orbiting electrons. The atom is the smallest unit of an element that retains its chemical properties. Understanding its structure is essential to understanding all of chemistry and physics. Our journey will span from Dalton's solid sphere to Rutherford's nucleus, Bohr's orbits, and finally into the mind-bending principles of quantum mechanics established by Heisenberg and Schrodinger. Let's start by exploring the early, foundational models that set the stage for modern atomic theory. John Dalton proposed atoms were indivisible spheres. Later, Rutherford's famous gold foil experiment revealed the tiny, dense, positively charged nucleus, overturning the, quote, plum pudding model. Niels Bohr introduced quantization, suggesting electrons orbit the nucleus in specific, fixed energy levels or shells. Electrons could only jump between these levels by absorbing or emitting fixed amounts of energy, or quanta. Bohr's model was a crucial step, but it couldn't explain everything. It paved the way for the radical ideas of true quantum mechanics. Louis de Broglie hypothesized that if light could behave as both a wave and a particle, then electrons, traditionally seen as particles, must also exhibit wave-like properties. This is wave-particle duality. Werner Heisenberg introduced the uncertainty principle. We cannot simultaneously know both the exact position and momentum of an electron. Erwin Schrodinger developed the wave equation, describing the electron's wave function and probability distribution. Quantum theory helped explain many observations that classical physics could not, particularly involving light and electromagnetic fields interacting with atoms. The photoelectric effect, where light ejects electrons, confirmed light's particle nature. The Compton effect showed that photons, when scattered by electrons, lose energy, reinforcing this particle-like interaction. The Stark and Zeeman effects describe how spectral lines split when an atom is exposed to an external electric or magnetic field, respectively, a phenomenon explained by quantum theory's angular momentum concepts. Now, let's turn our focus to the rules that govern the location and behavior of electrons within the atom, essential for chemical bonding. The location and energy state of an electron are defined by four quantum numbers: principal n, azimuthal L, magnetic m_L, and spin m_S. These numbers dictate energy, shape, orientation, and spin. The term orbit refers to Bohr's fixed path, while orbital is a region of space where there is a high probability of finding an electron. The shapes of s, p, and d orbitals are distinctly different, defining how electrons fill space. To predict chemical behavior, we need a systematic way to fill these orbitals with electrons, guided by fundamental principles. The Aufbau principle dictates that electrons fill orbitals, starting with the lowest available energy levels before occupying higher ones. This determines the ground state electron configuration of an atom. The Pauli exclusion principle states that no two electrons in an atom can have the same four quantum numbers, meaning an orbital can hold a maximum of two electrons with opposite spins. Hund's rule states that electrons will fill degenerate orbitals singly with parallel spin before pairing up. In conclusion, the journey from Dalton's simple model to modern quantum mechanics is a testament to scientific curiosity. The current atomic theory, with its orbitals, quantum numbers, and fundamental rules, is vital for understanding not just chemistry and physics, but the very fabric of our universe.